The second part of NODEMaple deals with Section 8 of the Eurocode, which deals with connections with metal fasteners. There are a couple of different fastener types like nails, bolts, dowels, screws, or special connections like shear connectors, bulldogs, split rings, sharp metals, and so on. So the chapter is quite difficult, and there are a couple of things we can go through. So I propose we just drop into the first example and have a look at that one. As I said, Section 8 in the Eurocode 1995-11 deals with metal fasteners, and I assume that you are familiar with what is part of this code, and we are going to go through some of the parts afterwards. The first example we are going to have a look at is still in Limtreboka. It's example 19, very easy. There is a metal connection put onto the beam which has a force of 65 kilonewtons pointing downwards. There is a distance of the connection in regard to the lower part of the beam. The beam size is listed here, the beam quality here, and the bolts are defined to be of 16 mm diameter with a quality of 8.8. Climate class is 1. So with these informations we can go back to Maple and note timber, opening the sheet number 8, connections with metal fasteners, and this is an error. Nice. So just need to do a reset here. This can sometimes happen when things have gone wrong, so we just open the sheet, timber, fasteners, Limtreboka example 19. Okay, so let's just go on. After the project information we have the system, and we are going from top downwards. So going back to the example, we usually have in a definition in an example of a connection we do have an outer part and an inner part. In that case the outer part is the steel, as the steel is fixed on the outside of the beam on both sides. It's not shown here, but it's explained in this graphics here. So we do have metal sheets on both sides, and we have bolts going through the connection. So going back to Maple, the outside material is steel and the inside material is timber. We have one inside layer with 0 tolerance between the layers. The finish is 4 mm steel and 190 mm timber, which gives a total thickness of 198 mm. The service class is 1, and low duration class is defined to be a short term. The Norwegian annex of the Eurocode gives these K-mod and gamma M factors. Here we do have information to fill in about the material. So as the outside material is not timber, this part of the connection is grayed out, so it's not possible to define something here. The inner part is timber, in that case it's called timber 2, a glulam timber GL30C. A grain direction is 0 degrees, which means that the grain direction is horizontal. The definition is to be of 119 and 1250 millimeters. Those on the left hand side just give you the standard dimensions we do have in Norway, with a weight of 90, 115 and 140. The 190 millimeters is of course possible to produce, but it's not in a standard format. So 190 by 1215. These parts on the right hand side define the geometry of the beam. So we are going to have a look at that one later. We're just going to go down to the result sections, and going away from the force is not so important. But what you see here is that the geometry shown is 500 millimeters to the left and to the right side of the origo of this part, and the cuts are 90 degrees perpendicular to the grain direction. So what is defined here is also shown here. So again, 90 degrees cut, 500 millimeters to the left of the origo, under same for the right hand side. The steel is defined to have a 90 degrees grid direction, which means upwards, 90 degrees from this one upwards. And we have a 90 degree cut perpendicular to the grid direction, 650 millimeters from the origo. Origo once again here, 650 millimeters would be slightly outside of the timber section. The right hand side cut is 50 millimeters from the origo on the right hand direction, which means from here upwards 50 millimeters. Other information are given here as well, so we just continue to the fasteners. The fastener input is very easy. You start on the top left and you go down and to the right. We have defined a bolt with 16 millimeter diameter, which gives you then the choices. There are two distributors of that one. The first one is a general one, it's just the ISO for T14. The other one is Rotoblasen, which is chosen here. We can pick either one of that one. We could use that one as well. Which gives you some error messages because we need a bolt which is bigger than the thickness of the system, of the connection. So 198 millimeters is the minimum length of the bolt. So I've chosen a 251 here. This one is usable for service class 3. We have a bolt grade 8.8. 16 millimeters, 250, 24. The green one are the ones that are chosen, the other ones are the ones that are standardized. We also have a washer with this size, and we don't have any shear connectors, so this one is just defined as not existent. The MYRK, the moment capacity, is 324 Newton meters. And the tensile capacity of the rod here is 125.6 kilonewton. The washer information, the internal and the external diameters and the thickness of the washer are given here. And this one is the NAXK, which is the characteristic capacity of the washer in regards to timber. As we do have a steel connection on the outside, the washers actually are not relevant. So let's just continue with the input of the fastener pattern. We do have a grid where the center of the washer or the fasteners is 100 millimeters below the origo. So this one is 100 millimeters, the center of the fasteners is 100 millimeters below. The distance of the fasteners is shown here, twice by 2 times 100 millimeters, which means that there is a distance of 100 millimeters here and here. So that already is enough to define the geometry, and we have a pre-drilled connection, of course, as it is a bolt. Check of the minimum distances gives those values. So we have 60 millimeters in the A2 direction. No, I'm sorry, this one is grayed out, not relevant. We do have 100 millimeters, of course. The minimum distance in A2, which is perpendicular to the grain of the timber, minimum would be 64, and the A3T is 500 millimeters and the A4T 408. For the steel, those are the minimum distances, which are, of course, no problem here. Going to the loads, we have entered a vertical load of minus 65 kilonewtons at a position 96010 of the origo. This one is also relevant because this is the check according to 814. In that case, 90% of this force are used to check F814. So if we go back shortly to the Eurocode, (814) is this check which does a splitting caused by a tension force. And this splitting check is shown in this diagram. There is a force on the section which is called FED, which in our case would be the vertical force, this one. But this is not the one that the section is dimensioned for. Actually, the section which is dimensioned for it is for these forces, if FVED1 or FVED2. And if you see a very simple static system with a beam with two supports, then a force in the middle would give a shear force which is exactly half part, the 50% of the force applied. So in that case, the reduction factor would be 0.5, and it also never can get bigger than 1, the force itself. So what you are entering here is actually a value between 0.5 and 1.0, a reduction of the shear factor. I've chosen here 90%, but of course you can put it to 100% as well. That's no big deal. So the next thing which we are going to do now actually is to have a check at the numeric values, and this program does the check of the capacity a little bit different than the Eurocode, because the Eurocode checks the connection itself. What I am doing here is I check each of the fasteners in the connection. So what we are seeing here is the force which is to the fastener which gets the most part of the force. Of course, in our case we just have 3 fasteners, and the force on each fastener is exactly 1/3 of the applied force. So this one is easy, but of course if you have a moment on the connection, then there might be one fastener which gets most of the loads and the other ones probably a little bit less. We come back to these examples a little bit later. So current load case 1 and the bolts with the maximum force is the critical node is the number 1, exactly the same as 2 and 3, so no difference here. Program chooses just one of them. And on top of that one we get the results of the calculations. So we have a calculated capacity of the bolt. We have also calculated capacity of the tension of the bolt. No overlap, a thin plate, FVRK according to 823 in the Eurocode with the formulas J till M, internal index S2SB. It is a bolt, which also is calculated as a bolt. We could have, for example, screws which are defined as bolts or otherwise. No double-sided connection as the bolt is going through the connection. We have pre-drilled. And it's also calculated according to 812 with a multiple fastener connection. So let's just get a little bit down first to the graphics again. The forces are putting downwards in that connection. This is quite important for one of the checks, and the check to have a look at is actually 814. As we have seen in the overview, the dimensioning part for the splitting force on the beam is the variable HE, which is the distance of the fastener furthest away from the edge in the force direction. So HE is going to be calculated, which is that one, 607.5 millimeters. In that case, it is the distance between this bolt and the edge of the beam. If the forces would change direction, I can do that by two ways. Either the first one is, of course, to go to the loads and put a plus in that direction. The other possibility is to check this box reaction force. This checkbox switches the direction of the force, which is going upwards now. So if we go back to HE, what you see now is that HE has increased to 807.5 millimeters because the new distance is from this bolt to the edge in that direction. So just check that you have the right direction of the forces for the splitting. So let's just move that one back again. We're going to have a look at that one. Annotations are 1, 2, 3 here for the force. We just put the forces away now. And we are going to have a look at the distances. Okay, so let's just go further on. We have the formulas for check of the capacity F, V, or K according to formula 822. This is actually probably not always correct because this also should include 823. 822 is a timber-to-timber connection, while what we are doing here is 823, the steel-to-timber connection. So I'll just going to fix that afterwards. So we have these formulas here, and going back to that one, we have a look at J, K, L, and M. So we're going to have a look at J, K, L, and M. All those ones are not relevant. These are simple timber-steel connections, while this is a steel-timber-steel connection. Okay. The minimum of those are relevant. That's the K one, and we also have the alpha rope factor because the bolts have washers and motor on the outside, so the tension capacity of the bolt is also something which is quite relevant here. So we have the 19 kilonewtons plus something in addition. F, V, or K is 38.1. Why is this one double? Because we do have two shear planes on that connection. This is for a single shear plane. This one is for the double shear plane. The dimensional forces is capacity here is of course this value multiplied by K mod and divided by gamma m. And the effective one is a probable reduction if you have a reduction of the fasteners in a row in grain direction. But as we do have no fasteners in grain direction, but all just perpendicular to the grain direction, there is no reduction of this one. So the capacity of one bolt here is 26.4 kilonewtons, and as we have seen, the actual load here is that one down here, 21.67, so that should give an utilization of 82%. The active check of the splitting force is 0.53, and we also have a check for the bolt connection, and the maximum of all those checks here is 0.82, so actually the check here is fulfilled. Let's just go a little bit down to the result details. I've told you that the 8.22 and 8.23 is listed up here. The alpha rope factor is 0.25. and outside part 1, as those are showing the capacity of the timber both on the outside and on the inside. We don't have any outside timber connection, so this is just on the right hand side. These are listed here. Just one additional comment to 8.14. There is the simple check according to the Eurocode. There is also a much more extensive check according to the German annex of the Eurocode. This one is also listed in Limtreboka, and this one is much better than the simple check here. So I'm actually giving both results here and using the best one, which means the one with the least utilization degree. But you're going to have to check that for yourself, which one of the tools you're going to use. If you don't want to have the check according to the German annex, then just switch that checkbox off. Okay. 6.2 is a check of the net section, which is not relevant here because we are not going to do a check in grain direction as well. So the steel and bolt checks here, they're also done into account, but the 6.2 net active is in that case just printed and not calculated here, but it's just calculated internally in the program, and the utilization factor is plotted on top here. So it might actually be a steel check which fails, but it's checked as well. And the block shear and block shear failure are not relevant here, as there is no block shear and block shear failure. We are dealing with forces 90 degrees perpendicular to the grain in that case. The other relevant factors which are basic for the calculation are also listed here, FH0K and so on. So that was a quick overview of the first example. Let's just go back to the example itself. Limtreboka has this split, right hand side calculation, left hand side diagrams and annotations. So let's just go quickly down here. I'm sorry. $16mm, these J, K, L, and M checks. Capacity of the bolts, which of course might be a little bit different because probably the steel quality which is used here is not the one which is available in my program. So let's just conclude this first example, and we'll go further on with other examples, not in Limtreboka but in a different calculation example from University of Technology in Trondheim. And I hope you'll see you next time.